Hello everyone. Today we will consider unsteady three-dimensional Navier-Stokes equations for laminar incompressible flows, and we will discretize this equation using finite difference method. In last class you have learned how to discretize the first derivative and second derivative of any variable. We will use a famous technique, marker and cell, proposed by Harlow and Welch to discretize these Navier-Stokes equations using finite difference method. So, let us consider these equations in Cartesian coordinate. So, for incompressible Newtonian fluid flow with constant properties, this is the continuity equation, this is the x component of momentum equation, and this is y component of momentum equation, and this is the z component of momentum equation, and this is the energy equation. In today's class we will just discretize the Navier-Stokes equations, and you can see how many variables are there: u, v, w, p. Okay, and if you solve for energy, then there will be temperature. So obviously you can see we have u, v, w for the Navier-Stokes equations and continuity equations. So 4 equations and 4 unknowns u, v, w and p. So to find the pressure, there are no obvious equation. We need to derive equation for to determine the pressure from the continuity equation. We will use the marker and cell technique, first proposed by Harlow and Welch, for solving free surface problems, and as we discussed in last class, we will use staggered grid. You know that in staggered grid, pressure and temperature will solve at cell center and velocities will solve in a staggered way. What is the advantage of using staggered grid? Because we will get a strong coupling between pressure and velocity. The differencing scheme for the momentum equations is basically just the forward time and central space FTCS method. And if we solve the system using u, v, w, p and temperature, then this system known as primitive variable approach, and here we will solve equation for pressure separately. So you know that first we need to discretize the domain into grids, so that we can solve the discretized equation in a discrete point. So if you consider this 3-dimensional domain, and you can see this is divided into grid, x direction is in this direction, this is the y direction and this is the z direction, and the grid we are giving the index with I, j and k. So you can see this is your j is equal to 1 and it is varying in this direction, and it is j is equal to j I m and previous cell is j r e. Similarly k is equal to 1, this is k is equal to 2, the last cell is k I m, and here we will apply the boundary condition at the last cell, and previous cell is your k r e. Similarly in x direction, this is the I is equal to 1, I is equal to 2, and this is the I is equal to I r e, and this is the I I m. So you can see your grid is varying I 1 to I I m, j 1 to j I m and k 1 to k I m, and boundary conditions will be applied at I is equal to 1 and I I m, and j is equal to 1 and j I m, k is equal to 1 and k I m, and the discretized equation we will solve in the interior domain. Discretized equation will be solved I is equal to 2 to I r e, j is equal to 2 to j r e, and k is equal to 2 to k r e. And you can see that in x direction we have uniform spacing of delta x, and in y direction we have uniform spacing with delta y, and in z direction we have uniform spacing delta z. So, grid size you can see this is delta x, delta y and delta z. So, this is the discretization of this domain. Now, we are considering unsteady equation. So, we need to march in time. So, we will march from n to n plus 1, where n is the previous time and n plus 1 is the current time or present time. So, the variables at previous time n are already known from the previous solution, and n plus 1 we need to determine. So, in MAC algorithm we use explicit method, that means there will be only one unknown and all other terms will be known from the previous time n. When we will go in time marching, so we will go from n to n plus 1 and your time step will be delta t. Okay. So, here grid size is delta x, delta y, delta z and your time step is delta t. So, now let us see the cell where we need to discretize the continuity equation as well as the energy equation and the staggered grid where we need to solve the velocities. So, you can see this is the main cell where at center you will solve for P, and this cell is I j k, index is I j k, and we need to solve for temperature. Okay. So, T I j k or theta I j k, where theta is non-dimensional temperature, and velocities. Now, you see we will solve in staggered way. So, this is the point where we need to solve for the velocity u I j k, okay, and this is the staggered grid where we need to solve for velocity v I j k, okay, and you can see in other direction we need to solve for w I j k. So, in that direction inside you will solve for w I j k, and this is the grid for w I j k minus 1. And now, if it is u I j k, so obviously this will be your u I minus 1 j k, and if it is v I j k, so here you will get b I j minus 1 k, and in the other face, the rear side, you will solve for w I j k, and this is the w I j k minus 1. So, you can see when we are solving for u I j k, so its neighbors are u I minus 1 j k and u I plus 1 j k, and for v I j k, this is the v I j plus 1 k and this is v I j minus 1 k. And you can see now in this main cell we will satisfy the continuity equation, and when we satisfy the continuity equation, so velocities just difference will be just del u by del x in x direction. So, you can see your continuity equation is del u del x plus del v del y plus del w by del z is equal to 0. So, this equation we need to satisfy in this cell where now del u by del x you can see that it will be u I j k minus u I minus 1 j k divided by delta x, because that is the first derivative discretization. Similar way you see this is v I j k minus v I j minus 1 k divided by delta y. So, you will get del v by del y. Similarly, you will can find del w by del z, and obviously you can see this is the grid size delta x, this is your delta y, and this is the delta z. Here you notice that when you have u I j k and this is your u I plus 1 j k, and at the center, okay, if you need to find the u I j k, so it will be u I plus half j k, and this is unknown. So, this unknown will be just solved using the average velocity using the neighbor points u I j k and u I plus 1 j k, and similarly for v and w. So, we have now discussed about the staggered grid and how the variables are stored in the grid. Now, let us consider the x momentum equation and discretize term by term using finite difference method. So, this is the x component momentum equation. So, first let us discretize temporal term. So, we will use forward time, central space, and you know that it is explicit method. Okay. So, first let us discretize temporal term. So, what is temporal term? This is rho del u by del t. So, rho del u by del t. Okay. So, now we will use forward time. So, this is first order accurate scheme. If you use, then you will can write u I j k n plus 1 minus u I j k n. So, we are discretizing with respect to time. So, that is why we are writing n plus 1 and here n and divided by the time step size. So, that is your delta t. Next, let us discretize the pressure term. Okay. So, pressure term if you discretize or pressure gradient term, okay, so that is your del p by del x. So, you can write p I plus 1 j k minus p I j k divided by, now you see. So, the distance between these 2 points is delta x. So, divided by delta x. Now, let us consider the viscous term in the right hand side. Okay. So, if you consider that term viscous terms. So, this is the viscous term. So, you can write this will denote as delta du. So, when we will write the discretized equation, we will use this notation. Okay. So, this is your mu del 2 u by del x square plus del 2 u by del y square plus del 2 u by del z square. So, you can see this is the second derivative of u, okay, with respect to x, y and z. So, you know the central difference scheme. So, this is the second order accurate. So, we can use the second order central difference approximation for this second derivative. So, you can write mu. So, del 2 u by del x square, what will be the discretized form of this equation? So, it will be u I plus 1 j k minus 2 u I j k plus u I minus 1 j k divided by delta x square. Okay. Similarly, del 2 u by del y square you can write as u I j plus 1 k, because with respect to y. So, in y direction you have this j plus 1, right. So, I j plus 1 k minus 2 u I j k plus u I j minus 1 k divided by delta y square, and the last term del 2 u by del z square. So, similarly, you can discretize like u I j k plus 1. So, in z direction. So, 2 u I j k plus u I j k minus 1 divided by del z square. Okay. So, this is the discretized form of this equation, and when we will use the explicit scheme, we will write del d u n, that means all these terms velocities will be from the nth time level. So, those will be known, right. Now, let us consider the convection terms. So, in the convection terms you can see you have del u by del x, similarly you have del u v by del y and del u w by del z. So, here two velocities are coming. So, one velocity is convected velocity. Okay. So, by the velocity is u v w, here u is convected, right, because this is the x momentum equation. So, we are solving for the velocity u, but velocity u is convected by velocity u in x direction, by velocity v in y direction and by velocity w in the z direction. So, you can see this term, if you see del u by del x. So, one is your convected velocity. So, here all these u are convected velocities and another u is just velocities which actually convecting this variable convected velocity. So, if you use central difference, then how you can use for this cell. Okay. So, this is your u I j k. Okay. So, this we will learn how to discretize this equation. So, here we will use some convection schemes. Because you have two velocities. So, one velocity we will calculate just at this face center, where it will be just average of the neighboring cells, but other velocity we will calculate using some convective schemes. So, there are different convective schemes are available, like first order accurate, first order upwind, second order upwind, third order upwind like quick, even you have central difference which is your second order accurate, and you can have the combination of these with some weighted function. So, here we will use convective scheme proposed by Hart et al. So, this is the scheme we will use, weighted upwind difference scheme, which is known as WUDS due to Hart et al. So, you can see we have del u by del x, right. So, what we will see, so this is to be discretized for the velocity here I j k. So, we will use u I plus half j k u star I plus half j k minus u I minus half j k and u star I minus half j k, and what is the difference between these 2 points? Delta x. So, here you see, here at this point we are discretizing this u term and we are discretizing. So, you can see this is the midpoint between I j k and I plus 1 j k. So, this point we are considering and this point, okay, which is your I minus half j k. So, you can see, so the distance between these 2 points is delta x, okay, but here we are velocity the velocities we are writing u I plus half j k and another is star quantity u star, okay. So, for the u star quantity we will use some convection scheme, and for u I plus half j k we will just take the average of velocities at I j k and I plus 1 j k. So, you can see in this case, so these velocities u I plus half j k, just we will use the average value, okay, at this point, taking the value from I j k and I plus 1 j k. So, you can write half u I plus 1 j k plus u I j k. Similarly, u I minus half j k you can write half. So, you can see at this point you want to find. So, you can use these 2 point values. Okay. So, it will be u I j k plus u I minus 1 j k. So, you can see it is just average value at this point we have considered. Now, this convected variable u star will use some convection scheme, and we are going to use this weighted upwind difference scheme. So, you can write this equation like del u by delta x as 1 by 4 delta x u I j k plus u I plus 1 j k square plus some factor gamma which varies between 0 and 1 u I j k plus u I plus 1 j k. So, we will take the modulus of these velocities into u I j k minus u I plus 1 j k, then we have minus u I minus 1 j k plus u I j k square, and we have minus gamma u I minus 1 j k plus u I j k this modulus and u I minus 1 j k minus u I j k. Okay. So, you see this factor gamma, it varies between 0 and 1. So, if you put gamma is equal to 0, what you are going to get? So, if you put gamma is equal to 0, so this term and this term will get 0. So, you are going to get actually central difference, because if you use central difference you will get this value for this convected variable. So, if you use that one, then it will be 2 and another 2 is there from this value. So, it will be 1 by 4 delta x. So, this square minus this square. Okay. So, these values. So, for gamma is equal to 0. So, gamma varies between 0 and 1. Okay. So, if gamma is equal to 0, you will get central difference method. Okay. So, this is your convection scheme, and if you put gamma is equal to 1, okay, so gamma is equal to 1, you will get upwind scheme. Okay. First order upwind you will get. What is upwind scheme? Let us discuss. So, if you see this value at I plus half j k you want to find, let us say u. Okay. So, now if at this point if velocity is greater than 0, u greater than 0, okay, then you consider the value of u at I plus half j k as u I j k. Okay. And if u less than 0, then you consider u I plus half j k. That means, if it is less than 0, so velocity is coming from right to left. So, you take the value of u at this point as same as this point u I plus 1 j k. So, it will be u I plus 1 j k. So, this is known as upwind. So, you are taking the upwind point from the direction in which the velocities are coming. So, you can see u greater than 0. So, u I plus half j k, you are taking u I j k value, and if it is u less than 0, so you are considering this value. So, similarly, here if u greater than 0, this value you consider as this value at I minus 1 j k, and if it u less than 0, then you consider u at this point as u I j k. Okay. So, this is known as appoint, and if you put gamma is equal to 1, you can see that you will get first order appoint, and if gamma is small, then obviously you can see it will be towards central difference. Okay. So, the discretized equation tends to center in space. Okay. Now, similarly, you discretize the other convection terms, okay, del u v by del y and del u w by del z. So, similarly, you can write del u v by del y as 1 by 4 delta y v I j k plus v I plus 1 j k u I j k plus u I j plus 1 k plus gamma v I j k plus v I plus 1 j k u I j k minus u I j plus 1 k minus v I j minus 1 k plus v I plus 1 j minus 1 k u I j minus 1 k plus u I j k minus v I j minus 1 k plus v I plus 1 j minus 1 k u I j minus 1 k minus u I j k. Okay. And this is the modulus. You know that if this value is greater than equal to 0, then it will return this value, otherwise if it is less than 0, then it will return the negative value. Similarly, you can write del u w by del z 1 by 4 delta z w I j k plus w I plus 1 j k u I j k plus u I j k plus 1 plus gamma w I j k plus w I plus 1 j k u I j k minus u I j k plus 1 minus w I j k minus 1 plus w I plus 1 j k minus 1 u I j k minus 1 plus u I j k minus gamma w I j k minus 1 plus w I plus 1 j k minus 1 u I j k minus 1 minus u I j k. Okay. So, you can see that using weighted appoint difference scheme, we have discretized the convection terms. we can write considering all the convection terms as delta C u is equal to rho del u u by delta x plus delta u v by delta y plus delta u w by delta z. Okay. And all these discretized equation we have already written. So, that you can write, and if you write delta C u n, that means we will consider u from the previous time level n, and in this discretized equation you can see whatever velocities are coming you consider from the known values at previous time level. So, now we have already discretized the temporal term, convection terms, pressure gradient term and the viscous terms. So, if you write down for the x component of momentum equations this discretized equation, then you can write like rho u I j k n plus 1 minus u I j k n divided by delta t. Okay. So, we are using forward time. So, it is explicit method. So, this is the temporal term. Now, we have convection term, okay, at time level n. So, we have already discretized this term, and we have pressure gradient term P I plus 1 j k minus P I j k. So, this you have to consider at n plus 1. So, this is your current time, okay, because you are solving the velocities at n plus 1. So, obviously, the pressure gradient term will be at n plus 1, but these are unknown, plus delta d which is the diffusion term at time level n. Similarly, you can write the discretized equation for y component and z component of momentum equation. So, you can write rho v I j k. So, this I j k for the V cell, okay, you have to remember this, because we have separate cells for u v w in staggered grid, okay, plus delta C V n and pressure gradient term. So, del p by del y. So, obviously, it will be P I j plus 1 k minus P I j k, okay, at time level n plus 1 divided by delta y plus delta d V n. And for z component of momentum equation you can write w I j k n plus 1 minus w I j k n divided by delta t plus delta c w n is equal to minus p I j k plus 1 minus p I j k at n plus 1 level divided by delta z plus delta d w n. We need to solve these equations. The pressure at current time level n plus 1 unknown, right. So, you cannot solve this equation unless you know the value of pressure. So, what we will do, we will assume the pressure, okay, some value. So, with this gauge pressure field obviously you will get the some provisional velocity. So, let us say that we are taking the pressure value from the previous time level n, and whatever velocity we will get, that is not the correct velocity field, but we will get some predicted or provisional velocity from the previous time level pressure values. Okay. So, now consider P at n level, n time level, and find provisional or predicted velocity. Okay. So, for u momentum equation, if you write, then you can write as rho and whatever predicted velocity is there. So, we will denote as u tilde, okay, I j k minus u I j k from the previous time level n divided by delta t plus delta c u n, and this pressure we are taking from the previous time level. So, p I plus 1 j k n minus p I j k n divided by delta x plus delta d u n. Okay. So, let us say this is equation 1 and this is equation 2. Now, you subtract this equation 2 from equation 1. Okay. Subtract equation 2 from equation 1. Okay. And you see that your u tilde, v tilde, w tilde, if you write for other momentum equations. So, these are provisional velocities. Okay. So, if you subtract, you see this u I j k at time level n will get cancelled, then you will get only rho u n plus 1 I j k minus u tilde I j k divided by delta t. These convective terms will get cancelled because it is at same time level n, and pressure term you will get p I plus 1 j k at n plus 1 minus p I plus 1 j k at time level n minus, now you have p I j k at time level n plus 1 and minus p I j k at time level n, okay, divided by delta x, and this diffusion term you can see it is same. So, it will get cancelled. So, finally, if you subtract equation 2 from the equation 1, you will get this expression. Now, let us tell that your corrected pressure. So, the difference between the pressure at time level n plus 1 and time level n will denote as a pressure correction, and this pressure correction you can denote as P prime is equal to P at n plus 1 minus P n. So, at I j k if you write, then it will be just P prime at I j k. If you write I plus 1 j k, then it will be P prime I plus 1 j k. Then you can write this equation as u I j k at n plus 1 is equal to u tilde I j k minus delta t by rho delta x, and the pressure you can write as pressure correction I plus 1 j k minus P prime I j k. Now, similarly, you can write this equation for velocity v and w as v I j k at n plus 1 is equal to v tilde, which is your provisional velocity, minus delta t by rho delta y, p prime I j plus 1 k minus p prime I j k, and similarly w at n plus 1 I j k, you can write w tilde I j k minus delta t by rho delta z, p prime I j k plus 1 minus p prime I j k. Okay. So, you can see that we have found the velocities at time level n plus 1 at point I j k in terms of the provisional velocity and the pressure correction term. So, you can see these u I j k you can write also in other grid point u I minus 1 j k and b I j minus 1 k and w I j minus 1 k. Let us write the continuity equation and satisfy it in the main cell. Okay. And from there we will substitute these velocities and we will find the equation for pressure correction, because that is unknown, right. So, once we know the pressure correction value, then we can correct the pressure P n plus 1 is equal to P n plus P prime. Okay. So, we can correct the value of pressure. So, now you can see the continuity equation will satisfy in this main cell. Okay. Here, okay, we will satisfy the continuity equation in this main cell. So, when you will satisfy, when you will write del u by del x, so it will be u I j k minus u I minus 1 j k divided by delta x, because the distance between 2 points is delta x. Similarly, del b by del y you can write b I j k minus b I j minus 1 k divided by delta y. Okay. And in z direction, now del w by del z you can write similarly w I j k minus w I j k minus 1 divided by delta z. Okay. So, you can see here u velocity we have found at this point v, and in the rear surface here w, and similarly you have u I minus 1 j k and u I plus 1 j k, here b I j plus 1 k and b I j minus 1 k, and similarly w I j k minus 1. So, now satisfy this continuity equation at this main cell. So, your continuity equation is del u by del x plus del v by del y plus del w by del z is equal to 0. Okay. So, now you write as u I j k minus u I minus 1 j k, and we are satisfying obviously at current time level n plus 1 divided by delta x plus v I j k n plus 1 minus v I j minus 1 k at time level n plus 1 divided by delta y, plus you have w I j k at time level n plus 1 minus w I j k minus 1 at time level n plus 1 divided by delta z is equal to 0. So, the value of u v w at n plus 1 we have found from this relation, you can see. So, the value of u v w at n plus 1 you can write in terms of provisional velocity and the pressure correction, and similarly you can write for u I minus 1 j k n plus 1. Okay, just you put here u I minus 1 and here similarly you just change the pressure. Similarly, v I j minus 1 k at n plus 1 you can find, and w I j k minus 1 at n plus 1, similarly you can write similar expression, and if you substitute it here, okay, u I j k and u I minus 1 j k at time level n plus 1 you are going to get. So, in terms of provisional velocity now we are writing u tilde n plus 1 I j k minus u tilde n plus 1 I minus 1 j k divided by delta x plus v I j k tilde n plus 1 minus v tilde n plus 1 I j minus 1 k divided by delta y plus w tilde at n plus 1 I j k minus w tilde n plus 1 I j k minus 1 divided by delta z, and you will have the pressure correction terms. Okay. So, that will be your minus delta T by rho. So, it will be 1 by delta x square, then you can write as P I plus 1 j k prime minus P I j k prime, and from the other point you can write from I minus 1 j k, that pressure term you will get as P I j k prime minus P I minus 1 j k prime. Okay. So, similarly for v velocities you will get this term delta y square. So, we will get p prime I j plus 1 k minus p prime I j k minus p prime I j k minus p prime I j minus 1 k plus 1 by delta z square p prime I j k plus 1 minus p prime I j k minus p prime I j k minus p prime I j k minus 1. Okay. So, you can see the first three terms, okay, this term and this term. This is actually the continuity equation for the velocity for the provisional velocity, but obviously when you are starting the solution, provisional velocity will not satisfy the continuity equation, but when the solution will converge, then u n plus 1 will be your u tilde, v n plus 1 will be v tilde, and w n plus 1 will be w tilde, because the provisional velocities will be same as the velocities at time level n plus 1. So, it will satisfy the continuity equation. So, you can write these three terms as a divergence form. So, if you rewrite it, and you can write after rearranging divergence of u tilde vector. Okay. So, this is the term we are writing. So, this is the divergence, because this is your divergence of u, right, is equal to 0. So, we are writing these three terms, okay, in the divergence form, divergence of u tilde, okay, and you have minus, you can write as delta t by rho, after rearranging you can write as p I plus 1 j k prime minus 2 p I j k prime plus p I minus 1 j k prime divided by delta x square. Similarly, you can write p prime I j plus 1 k minus 2 p I j k prime plus p I j minus 1 k prime by delta y square plus p I j k plus 1 prime minus 2 p I j k prime plus p I j k minus 1 prime divided by delta z square is equal to 0. So, this will be equal to 0, okay, because we have substituted it in the left hand side. So, yes, right hand side is equal to 0. So, this is equal to 0. So, now in the right hand side it will be 0. So, you can see here we will assume that pressure correction in the neighboring cells are 0. Okay. So, in Mach algorithm, it is assumed that the pressure correction in the neighboring cells are 0. Okay. So, under this approximation, okay. So, you can see, so all these terms you can make it 0. So, this term is 0, this term, because neighboring cell pressure correction we are just taking 0 for simple calculation, and that is your Mach algorithm. So, if you put 0, then you can write the equation for pressure. Okay. So, divergence of u tilde minus delta T by rho, okay, and you will get minus 1 by delta x square minus 1 by delta y square minus 1 by delta z square, and we have taken outside 2 p prime I j k. So, you can see now this is the equation for pressure. Okay. So, you will get the pressure value from this equation. So, you can write P prime I j k. So, you can find it. So, you see minus minus plus, and if you take in the other side, then it will become minus divergence of u tilde vector, where u tilde vector obviously you can see it will be u tilde I plus v tilde j plus w tilde k. Okay. And now you can see in the denominator you will have 2 delta t by rho into 1 by delta x square plus 1 by delta y square plus 1 by delta z square. So, you can see that we have already discretized the equations for the momentum, and substituting those in the continuity equation in the main cell, we have found the equation for pressure using Mach algorithm. So, in the Mach algorithm we are neglecting or assuming the neighboring cell value of the pressure correction as 0, and following that you can write the equation for pressure as this. Okay. So, once you find p prime, then obviously you can correct it. Okay. So, you can correct p n plus 1 I j k as p I j k at nth level plus p prime I j k. Okay. So, this if you solve, then obviously you will be able to find the values for the velocity u I j k n plus 1. Once you know the pressure correction value, then you can find from the provisional velocity minus delta t by rho delta x, okay, p prime I plus 1 j k minus p prime I j k, then v I j k at n plus 1, you can find v tilde I j k minus delta t by rho delta y, p prime I j plus 1 k minus p prime I j k, and w n plus 1 I j k is equal to w tilde I j k minus delta t by rho delta z p prime I j k plus 1 minus p prime I j k. So, once you know the pressure correction values, and from the known provisional velocities, you will be able to calculate the velocities at n plus 1 level. in the pressure equation to accelerate the calculation P prime I j k, some over relaxation factor is used. Okay. So, you can write W naught, which is your over relaxation factor, divergence of U tilde. Okay. So, this obviously at I j k of main cell divided by 2 delta T by rho 1 by delta x square plus 1 by delta y square plus 1 by delta z square. Okay. So, here this W naught is known as over relaxation factor. Okay. So, to accelerate the calculation, okay, over relaxation factor may be used. Okay, and omega naught value generally of the obviously it will be greater than 1. So, you can write of the order of 1.5 or 1.6 in that range. Okay. So, in today's class we have used finite difference method to discretize the Navier-Stokes equations using Mach algorithm. We have actually used staggered grid to discretize these unsteady Navier-Stokes equations. We have used finite difference method and written the difference equation for first derivative and second derivative using Taylor series expansion, and we have used forward time and central space, which is your explicit method. After discretizing the each terms, temporal term, pressure gradient term, viscous term and the convection term, we have written the governing equations, but pressure at n plus 1 level is unknown. So, we have assumed the pressure from the previous term level and we have solved for the provisional velocities first. Then once you know the provisional velocities, then you substitute it in the continuity equation in the main cell. Once you substitute it, you can get the pressure Poisson equation, but if you neglect the pressure correction of neighboring cells, then you will get the equation for pressure. Once you can find the equation for pressure correction, then you can find the pressure at n plus 1 time level after correcting the values from the previous time level p value, and you can find the velocities at n plus 1 time level from the provisional velocities and the pressure correction terms. Sometime this pressure correction equation you can use the over relaxation factor to accelerate the solution, and this over relaxation factor generally or commonly it is used as 1.5 to 1.8. Thank you.